and very good morning, good afternoon, and good evening for different time zones. Welcome to the third seminar organized by the Hong Kong U Laboratory for Systems Analytics. And I'm Ray Zhong from the Department of Industry and Manufacturing Systems Engineering. So today, we are very honored to invite Professor Wang from KTH to give a talk. So I would like to introduce Professor Wang. Professor Lihui Wang is the chair of Sustainable Manufacturing at KTH, Royal Institute of Technology, Sweden. His research interests are presently focused on brain robotics, which will be, today's topic, cyber physical systems, real-time monitoring and control, predictive maintenance, human-robot collaborations, and adaptive manufacturing systems. Professor Wang is actively engaged in various professional activities. He is the editor-in-chief of several reputable journals, such as International Journal of Manufacturing Research, Robotics and Computer Integrated Manufacturing, as well as Journal of Manufacturing Systems. He has published 9 books and over 500 scientific articles. So productive. Professor Wang is a fellow of Canadian Academy of Engineering, CIRP, SME, and SME. He is also a professional engineer in Canada, the president of North American Manufacturing Research Institute of SME, and the chairman of Swedish Production Academy. So today, Professor Wang will give a talk on brain robotics for human-robot collaboration. So let's welcome Professor Wang.
Thank you, Ray. I'm trying to share my screen.
Please.
So thank you again, Ray. I think this is a good opportunity for me to share this topic together with you. I can see there's more than 100 people joining this meeting. And I'm sure there's many people I know, old friends, but also it's opportunity to meet new friends, new colleagues. I'd like to first thank Ray for the invitation and for your colleagues in the University of Hong Kong. Thank you very much. And go through the presentation today, as Ray already mentioned, the topic is focused on brain robotics. Some of you may not be familiar with this term. It's relatively new. Use a brain to control robot for human-robot collaboration. So this is brain robotics. Let me turn on my laser pointer. So here you can see the spinning logo. This is also the logo of our laboratory, symbolize the human and a robot working together as a team. And also could be digital physical, cyber physical, and so on. This is a hot topic today. You know, Sweden is located in the northern part of Europe, and KTH is located in capital, Stockholm. Today, I wanted to share with you first the historical background and talk about the basic concept of brain robotics, and then go through 2 application scenarios. One is on motor cortex-based brain-robot interface. The other one on brainwave-driven human-robot collaboration before I finally conclude this talk, highlight some future research directions. This is part 1 of my presentation. Per the request of Ray, I will also share part 2 is more related to journal matters, how to publish in several well-known manufacturing journals. So first part is some historical background. We need to understand the natural intelligence and the human brain better so we can conduct our work with basic knowledge. Some of you perhaps already know, we are looking at the intelligence science. Intelligence science have two branches. One is natural intelligence. The other one is artificial intelligence. So the source of artificial intelligence is a natural intelligence, which investigate and study the nature, living algorithm, and also their behavior. So in the natural environment, there's many intelligence already exhibited through long evolution process, and artificial intelligence is triggered by that. However, with the improvement and a new AI algorithm, it also help people to further study, investigate the phenomena and science in the natural intelligence. So this is two helping each other. And this is one of my favorite diagram. After reading a very thick book, I generated this diagram. So it's a brief history of AI. As you can see, the history of AI can be traced back all the way to 1943. The AI history and went through 4 different stages. The first one is the dark age, and then goes to the rise of AI, and then deep down, going to the so-called AI winter. And then in the early 80s, AI becomes a science and research activity took up rapidly. So I just wanted to go through several examples due to time limitation. The first one, this is important, binary ANN. So this one was first reported in 1943 by 2 researchers in University of Illinois. So they only considers on and off 2 states for each neuron. So that's the beginning. And machine can think. This has been proved by Alan Turing. So Turing test is also well known. This is in the 1950. 1951, 2 graduate students from Princeton University developed the first neuron computer. And this computer can simulate a network of 40 neurons at the time. So the most interesting thing is this was developed by 2 graduate students. 1956, there's an important event, the first AI workshop. This workshop was organized by John McCarthy from Dartmouth College, also in the USA. And several dozen of people attended this workshop, and John proposed to use artificial intelligence, or AI in short, for this research area. And all the participants agreed to use this terminology, and we continue to use it until today. So this event means the end of a dark age and also the start of a second phase, the rise of AI. Later, John moved to MIT and developed Lisp language for artificial intelligence related research. Fuzzy set was reported in 1965 by Lofty Zadeh. He's from UC Berkeley. 1969, first expert system was developed in Stanford University. And this project was sponsored by NASA. However, at that time, the problem this type of expert system can handle is relatively simple, or like toy problems. And this Dendro project was canceled. And similarly, several other AI-related research project has been terminated by the funding agency as well. This is why AI went into AI winter. Nevertheless, research activities still was ongoing. In 1975, genetic algorithm was first reported by John Holland. He's from University of Michigan. So he introduced the selection, mutation, crossover as the basic genetic operators. We still use them today. And another expert system is called MySyn. This is from the same group of Stanford University. And they use 450 different if-then rule to determine the root cause of a blood disease. And this system actually works much better than a junior doctor and also shows the promise. And further, later on, there's backpropagation and learning was implemented in neural networks. And 1987, fuzzy logic and fuzzy set theory has been successfully implemented in home electronics by some Japanese manufacturers. Example including rice cooker, washing machine, dishwasher, and later used in cars as well. And intelligent agent was quite popular in 1995. And more recently, we have a different optimization algorithm, like on the colony optimization, particle swarm optimization, AIO, DNA computing. So something, excuse me. Something interesting is before application in industry, there's a time span. Normally it's several decades. When fuzzy set was first reported in 1965, it reached the industrial application 22 years later. So whatever we are doing today, perhaps if we believe it, we will find the application potential in the future. This is also the vision for this brain robotics related research. May not see the immediate application. And in the future, more and more will go to brain and try to figure out how the brain power can be used for industrial application for robot control as well. Some examples summarized here as an early AI application. Gary played chess with Deep Blue. Deep Blue is a computer program of IBM. Eventually, Deep Blue won the game. And in 2005, Honda Asimo was demonstrated on stage, and this robot can walk up and down stairs controlled by a human standing on the stage. For this to work, the robot needed to have a voice processing capability to understand the command issued by the human commander, and also needed to have a vision, recognition, cognitive analysis of surroundings, needed to understand the height of the stairs, to do dynamic planning of a path, motion planning as well, try to keep a balance. And all those need some support from artificial intelligence algorithm. And people may think this is excellent, wonderful, but think about a child. A child of 5 or 7 years old can do the same job very rapidly, and you can even skip steps, can jump. This is a level of AI about 15 years ago. A little bit later, 2011, IBM developed this Watson program. The Watson program is to receive a question and generate an answer, and just one answer that should be 100% correct. And eventually, in this year, 2011, Watson won the competition in Jeopardy. So I will not go through the details. There's a processing process needed to be followed. You can find more details through online search. AlphaGo is another very important event in 2016, and AlphaGo competed with Go champion Liseto in South Korea, and eventually AlphaGo won the game 4-1. And behind this game, there's a cloud server located in the USA using 1,920 CPUs, 280 GPUs, and simultaneously use 64 searching threads. And it is a big data problem. There's 30 million different moves. And AlphaGo needed to find one move that has the higher risk winning probability. And for every move, needed to calculate a number of different possible moves. And human cannot compete with machine. How to do that? It uses reinforcement learning, use Monte Carlo search, and combined with a deep neural network. Furthermore, there's AlphaGo Zero, learn between themselves from scratch. And after 3 days, it reaches the level of AlphaGo. After 21 days, reaches the level of Kejie of another Go champion in China. After 40 days of self-learning, no human being can compete with this computer game. So there's different machine learning models and method. It is summarized in this table based on whether the algorithm is supervised, unsupervised, or semi-supervised, or whether it's a discriminative or generative, use deep learning or non-deep learning approach. If we have all those different AI algorithms and we have data from the real world, what can we do? The data can be collected from sensors, from robot controllers, from smart tools, or even from a historical database. So the data is passed on to the machine learning models. After processing by the suitable, appropriate machine learning algorithm, the data can be converted to knowledge. And this knowledge is further used to domain-specific applications. For human-robot collaboration, HRC, perhaps we can use AI algorithm for assembly parts recognition, for human activity recognition, or for human motion prediction. And with that, can support action of a human to do the assembly job. Now let me move the topic to the basic concept of brain robotics. Why we need brain robotics to help us? First, let's look at a bigger picture of a human-robot collaboration. Normally, robot is controlled by native code. The code is generated well in advance. But when human and robot work together is in a dynamic environment, we cannot use pre-generated code because there's zero flexibility. The code should be generated on the fly. And also, robots should learn from human operators over time, getting better and better. There's different ways to control robot in addition to rigid code. It is possible to use different gestures, to use a voice, and use a haptic control without a haptic sensor, just patting the robot hand effector. And if a robot can detect the meaning, then can respond. Or alternatively, we can use a brainwave because no matter its a voice or its a gesture, it's controlled by human brain. If we understand the source of a human brain and use that signal directly to control the robot, it's a shortcut. Because for human being, gesture and speech make sense. For robot, doesn't make any sense. Human brain is very powerful. Human brain has more than 86 billions of neurons. It's a complex network. And neurons send and receive information. And between the small sections, there's a so-called synapses. So there's an interface here called synapses. And the electrical charge can accumulate it here to pass the information from one section to another section. And this is done at rapid speed. And no matter we see, we feel, we touch, or we think, everything is carried out and sends the information through this neural network inside of a human brain. If we use an electrode to properly detect and collect this brainwave information, process them, understand them, we can find more details about the human thinking. When we think, there's a different frequency we can consider. If we are in a deep sleeping mode and the curve is in low frequency, up to 4 Hertz, and without a dream. Similarly, if we are sleeping, but with a dream, this frequency is from 4 to 8 Hertz. So this is a theta wave. The previous one is a delta wave. We are not interested in this frequency. However, for alpha wave, this is more meaningful. Human is in a calm environment and thinking about something from 8 to 13 Hertz. Another wave range is a beta wave from 13 to 30 Hertz. This is also in a wake working environment. Further higher than this frequency, there's a gamma wave. That is when human being is being threatened, you generate a high frequency wave. Those signals can be used to protect human to trigger emergency stop. So this is important to understand the frequency range. And also there's a different portion inside of a brain. Because of time, there's no time to explain the detail, but by the name, you can associate with the number here. There's a frontal, prefrontal, parietal, central, occipital, and temporal. Different sections of the brain is for different signal processing, some for motion, some for speech, some for memory. And when we think certain things, this is a scenario when a gentleman looking at some medical surgery operation, and he may trust or may generate certain concerns. So these different brain sections is interrelated to each other, passing information around. So this is also related to the use of which channel, which electrode to collect information from which part of the brain. This is still unknown relatively, even in the medical field. Right now, there's a different EEG devices. EEG stands for electroencephalograph. And we can use Jellyfish is a commercial device, or use Epoch Plus, or use G Ladybird. And in our laboratory, we have this device, this headset. It's from Nautilus EEG headset. And this device shows 64 channels, but we use this cheaper one, only have 16 channels. And from the property or functionality perspective, the signal to noise ratio compared with the other devices is much better in the gray zone. And proportion of artifact is also good. And the red area is not so good. Using this headset, the electrode can collect brainwave signals and pass it to a box mounted at the back of the head. And the signal is hardware amplified and use Bluetooth to send to a nearby computer for further processing. However, during this process, a number of different artifacts are added to the raw signal. This including biological artifact, electrode artifact, electromagnetic artifact, or even electronic artifact. And this eventually needed to further be amplified and converted to digital data for further processing. So bottom row here shows the process chain from signal acquisition to artifact removal and extract the features. This is important. And in real time, when we use the brainwave signal, it needed to be classified to match to identify the feature and send it to robot controller for control. So this is the main process. Because of time, I need to skip some of the slides. This is a EEG signal acquisition. One thing I needed to mention is brainwave signal is very weak at the microvolt level. This is why the signal needed to be amplified and then do the processing, as I mentioned earlier. There's 16 channels. Also, there's 2 additional channels. One is ground electrode, and another one as the ear tip is used as a reference. So what the headset collected is a relative voltage potential compared with a reference point at every second when data is collected. The range of this sensor is at millivolt level. However, the resolution goes with this range and getting loose and loose. So resolution, if a range is 187.5, resolution is higher at 22 microvolt. So we need it. So this range can be selected from the configuration software when you use the headset. So this is the environment set up in our laboratory. We have a robot, controllers are connected to the central computer, and headset for EEG signal collection is also connected to another computer. Of course, there's a firewall to protect. So in the future, this electrode headset can be embedded into a helmet for safety protection. So operator can wear the headset at all time, can collect your brainwave. So it's practical. Now I wanted to go to 2 research topics. The first one is a motor cortex-based brain robot interface. This is for some basic investigation at early stage. Motor cortex is this part of the brain. If we take half of them at a different location, the motor cortex is for different movement. Somewhere is for hip, here is for foot, and for tongue, and so on. So different part of the brain is for different motion control in a sense. And of course, there's a hardware and a software environment. This is a headset we have. What you need to understand is the placement of electrode. The red spot is where the sensor is located. It follows this 1020 map. The objective is to receive raw data through pre-processing and try to extract the features, eventually generate a trained model or pattern. The training needed to be done in advance through multiple sessions, and each session normally is around 8 to 10 seconds, and need to go through a number of different sessions. The training in this case is use electrode to collect your brainwave signals. At the same time, use MATLAB to generate 1, 2, 3 random number, 1, 2, 3. And it's visualized on screen, this arrow, pointing left, pointing right, pointing up. And when the people for the training see this signal can move left hand, move right hand, Well, this is a stick town. And so all the data collected is labeled with 1, 2, and 3. Let's look at the signal collected and recorded. You can see here, there's quite a lot of noise. This is generated by eye blinking. The sensor is very sensitive. If you blink your eye, generate lots of noise, and this needs to be ignored or removed. And also there's one channel is not performing well. Perhaps it's not connected to the skull very well. This channel need also to be ignored. And here you can see the labels 1, 2, 3. And in between is related to you move your left hand, right hand, or stick your tongue. And it is also possible to visualize them, use this power topography map. And you can see the potential, power potential distribution over the head. The other objective is for online usage for signal processing. The data is still received from the sensor set and sent to a server and try to classify it and identify the right command, whether it's a left arrow or right arrow, so robot can move accordingly. So this is just a simple example. We tested a different algorithm and found this one, spectrally weighted CSP, is a common spatial pattern, is most reliable compared with other, but still the accuracy is not that high. It performs the best, but the accuracy is only 78.4%. There's a large range of error as well. The training time is moderate and can support real-time application. After that, we did a further test at brainwave-driven human-robot collaboration, and this time we use a different sensor set available in our laboratory. It's Epoch Plus from Emotive companies called Emotive. And this sensor, at the bottom, you can see the waveform from different channels. I skip them. And it's a sensor placement at a different part of the head. And also follow this 10-20 system. 10-20 system is the spacing between the sensor needed to be 10% or 20% from front to the back, from left to right. So it's equally placed. You can select one of them, but hardware design already configured that. If you select a device, it's better to check this map. And this is another view from left side, from right side for this sensor. The interesting thing is when we try to think about a control command, we may think move. The move can be in the language form. Even so, you do not speak, you think about a move as a language. You use one part of the brain. Or you may think about moving, can imagine moving the robot. So depends on how you use your brain. Actually, the brainwave change. The brainwave form also change. You actively use a different part of your brain. This is most the tricky part. For every individual, need to go through the training process in order to capture how the individual use the brain that way. This is, I mentioned earlier, we can visualize at a time t, how the distribution of a power potential is over the head. The red is higher, the blue is lower in terms of power potential. And this is relative to the reference point. And the bottom here shows the frequency and the weight. At one time, the signals from different frequencies, some area with a higher volt, some with a lower volt. However, use a brainwave to directly control robot is very challenging, it's difficult. What we use is use a micro control approach. So here we introduce a function block. In order to do this type of assembly, to pick up pin and insert in the hole, how to generate a trajectory and specify the speed and so on, veer point, all those is generated by function block. So function block has an input and has an internal algorithm. And this is driven by different event, follows a finite state machine. Eventually, brain signal is to trigger the right function block, and the function block, for example, related to move, can generate where to move and how to move, and may have an internal algorithm for trajectory generation and so on. So some of the information is from the environment, like a position of the pin. This is known. And this endpoint is also known. Some of the obstacles along the path can be detected by other sensors. So the algorithm needs to figure out, pick up a pin, avoid collision with anything along the path, and use a certain speed, orientation, insert the pin. This is controlled by function block, but it is triggered by brainwave. So I show you some examples. So I skip the detailed processing part I already mentioned earlier. Here shows a snapshot. So my former student is doing the experiment. Think about the command, and the robot can be moved. So this is a user interface he can see. For security reason, he hold a computer just to accept or reject a certain command if it's not safe, to avoid a collision between robot and the environment. And here shows a different waveform in different frequency. I think I reached almost the end of part one. Let me conclude. So a brainwave-based approach can be used for human-robot collaboration. Brainwave can be used as an additional modality in addition to voice, gestures, haptic control, and so on. So brain and robot, in this case, brain can be monitored and also can be used for control the robot, and can also to get engagement between the human operator for task execution with the robot together. Brainwave, if we detected some very strange signals, maybe that's related to the tiredness level where the operator is scared by certain things. Those can be used for robot control speed limitation to reduce the speed of a movement of a robot or stop it. This is especially in a panic level for the gamma wave. So we introduced the multimodal based communication and also introduce the macro-micro control approach. So there's many uncertainties, unknowns in this research field. And we wanted to continue to work in this area. Hopefully it will become feasible and practical in the future. There's some good news is from Link of a Neuralink company from Musk. And if you take some small surgeries to embed the chip into the skull, it can provide 124 electrodes in a small area, and the data is more accurate. But this is invasive and need some operation as well. So this is pretty much what I wanted to share with you. If you are interested, there's two relevant papers we published before, and it's listed here. So this concludes the first part of my presentation. So Ray, do you want to go directly to the second part, or you want to take some question here?
Okay, thank you so much, Professor Wang. I think we can go ahead for the second part. And at the end, the audience can ask any questions related to these two topics.
Okay, so I will. I will turn on my second presentation. Give me a second. I need to find the panel.
Take your time. And I think my colleagues, Professor Henry Lau is here, and Dr. P.C. Chen.
Okay, nice to meet you all. And I will start the second part. This is also from the request of Ray to share some of you the publication-related issue. I'm currently serving as the editor-in-chief for Journal of Manufacturing Systems, Robotics and Computer Integrated Manufacturing and the International Journal of Manufacturing Research. So I will use GMS as an example to walk you through some important issue. Of course, I need to promote the journal a little bit. You know what's the impact factor. The current impact factor for the journal is 5.105. This is the latest for 2019 impact factor. So it's in the quartile 1 for all the 3 categories that this journal belongs to. This is from Journal Citation Report. You can see the rank is pretty high, 5th among 83. This is 7 among 50 and 5 among 48. It's the evolution of an impact factor. First impact factor is 1997, and last year we got this 5.109, and I became editor-in-chief last year. So see this increase. Very happy to see that. In terms of journal performance, and this chart shows the submitted manuscript and editorial outcome. So first row shows the performance of a different year. Let's take a complete year of last year as an example. This is a year to date, not complete. The submitted paper is in orange, rejected paper is in navy blue, accepted paper in green, and this is a withdraw paper, about 20, and finally published paper. So you can see there's a difference between accepted and published. This is because there's accumulation from a previous year, especially if there's a special issue, we need to wait for the special issue complete and publish. So sometimes goes high, sometimes goes low compared with accepted paper. And in terms of rejection rate, it's quite high. 77% of the submissions are desk rejected without review. That's rejected by the editor-in-chief. And 12% of the papers are rejected after review. So altogether, you can see the acceptance rate is very low, only 77 papers. And there's many others statistics, I skip them, but I wanted to give you some suggestions from my perspective. And one interesting thing was a favorite quote is this one. This quote is from Roman Emperor Marcus Aurelius. He mentioned, everything we hear is opinion, not a fact. Everything we see is a perspective, not the truth. We need to understand. Reviewer and authors are standing at a different side. One says 4, another says 3. Both of them are true. But how to convey your message properly? Try not to mention your opinion, your perspective in the paper. Focus on the fact and the truth supported by data. So this is important. So when we submit a paper, of course, focus is to submit original high quality work of yours and be relevant to the focus area. For every journal, there's a focus area. You can check the aims and the scope of the journal. Otherwise, the paper might be rejected based on out of scope. And the writing of the paper needed to be logical, to be concise, and error-free. This is related to how careful you are as an author. Writing good English is not sufficient. Need to be logical, follow a logical flow. Need to be convincing. That's important. And also need to have a critical analysis of a journal's previous publication. This is also the relevance. Why you wanted to publish your paper in this particular journal. Every editor and publisher wanted to see the relevance. The readership of this journal also wanted to see the relevance. Why there's so many different journals and you choose GMS, for example. Need to have a comprehensive literature review, at least 30, to justify why this research is important, why you want to take this approach to tackle the problem, and what is the breakthrough, because you need to identify the gap in the literature where your work can bridge the gap and improve it, no matter it's incremental or it's disruptive. And need to have professional diagrams. Often I see manuscripts submitted with very poor quality of diagrams. Even the line segments are not meeting together. It shows the symptom of a carelessness. So those need to be avoided to have a professional diagram to support your presentation in language, in text. And also need to follow the author's guideline, write in good English. So among all my recommendations, English is the last one. It's less important to me. Technical writing, you do not need to be very fluent. Good English is good enough, but need to be logical. That's important. And you tell a good story. And by doing this, if you follow these suggestions, you encourage a reviewer to read instead of after 3 minutes, they try to find weak point, try to reject the paper. Encouraging reader to read is very important and can also shorten the review process and increase the success rate of your submission. So I wanted to show several diagrams that supposed to be published in a paper in archival journal. This is a level of diagram should be included. Whenever you draw a diagram, make sure they present in a professional way. So I leave 10 minutes for questions. By the way, this journal also have a best paper and one best paper per year. So there's a criteria already published online. You can check as a journal webpage. And by submitting your best work, best paper, there's a possibility this paper is popularly cited and you can get a best paper award down the road. Mentioned earlier, I'm serving in other editorial board as well as the editor-in-chief for RCIM, IGMR, and also associate editor for IJPR. Thank you very much. So I think we can go to question and answer.
Okay, thank you so much, Professor Wang, for these two topics. The first is the brain robotics, and the second one is sharing some insights about the editor-in-chief, looking at the different submissions. Okay, so we got some questions. So audience, please feel free to type your questions through the chat channel, or we still have a Q&A session. You can click and place your questions over there. So first of all, let's have a look at one of my colleagues, Dr. P.C. Chen. He asked, Ray, I have a question for Professor Wang. Is a brainwave generated by moving an object the same as the brainwave generated by thinking about moving the object? If so, how to translate the later brain wave into the former brain wave so that the robot can understand?
Mm-hmm. Yeah, this is a very relevant, good question. Thank you. This is a tricky part. I mentioned earlier, every individual uses a brain differently. And through the training process, you need to be in a very calm, quiet environment to think about your control command. It's a move. Perhaps you, for this individual like myself, I try to use a language like English, move. I think move as a language. And through this training, your brainwave is recorded. If that's the case, the individual needed to be consistent in real time when controlling the robot. Better not to think the imaginary movement of a robot moving around, then that command is not good enough, may not be triggered properly. So this training process is very important and need to be consistent to use a certain part of your brain. So if the training doesn't have that part of information, it's difficult to use. So individual will show the difference. This is why, as I mentioned earlier, the accuracy is less than 80%. But through more data for training and retraining during the day, because you use the data repetitively, and the data size is larger, and gradually it covers all different type of thinking you may use, and eventually use the matching algorithm to identify the right pattern. If you have a both word-based move or imaginary move, then it can pick it up. But the brainwave form will be different. Hope I answered your question.
Yeah, PC, you can unmute yourself.
Yes, thank you, Professor Wang. Yeah, it's very clear. Thank you.
Thank you.
Thank you. We have two questions from the Q&A channel. So audience, please indicate yourself, your name, and which university or institute you are working at. One question is from Zhang Zhongfei. Professor Wang, the brainwave control robot is in the laboratory stage. Does it take a long time to land before the industry application stage? What are the main challenges? What's in your opinion?
Thank you for the question. When I show this brief AI history for FajiSat, it took 22 years. For brainwave, I guess perhaps it take a similar amount of time before it can be practical in a factory environment. So in laboratory, you can control the environment to be less noisy and less disturbance. But in reality, in a real factory, this is very difficult. There's lots of noise, and human being after training still cannot concentrate to generate the same time of control command in a quiet environment. This is very challenging work, but I believe over years there will be new sensors, different headset to be developed. The hardware will be better, less noise, and more reliable, may have more channels, and we will understand the brain much better. If we try to use a language to control a robot, perhaps we can just use a certain electrode and with a high weighting factor. And that's one way to increase the accuracy and also speed. So the big challenge right now is the interference in the factory environment and the low accuracy of a current hardware and software. So it takes some time, but this will show some potential, especially for human-robot collaboration. Thinking about robot and human doing the job at the same time, and the worker is occupied and cannot use a sign language to control the robot. You are holding a heavy object, and the robot need to come over to help you. and use language in a noisy environment is not reliable either. So that's why to use this. But if environment permit, it is possible to use a multi-modal control approach to combine brainwave with speech, with gesture whenever it's possible. So this redundancy can increase the accuracy and reliability.
Okay, thank you so much, Professor Wang. Another question in the Q&A channel is from Kevin Kerrigan. Thank you very much for the fantastic presentations. My question relates to the social effects of such technology when introduced to the factory setting. What's the expected effort of this type of technology on the behavior of production staff, both in their interactions with others and their own personal thought processes? Further, is brain control a new skill that manufacturing engineers should be preparing for?
Yeah, this is a complicated question. It's a good question as well. And related to the social aspect, there's also some legal aspect because this is collecting privacy information from the individual. And if the purpose is right, is lawful, it is possible to use this because every worker needs some training, need to sign occupational agreement to work in that environment to allow sensor data to be collected and used to improve efficiency, protect human safety. So that part should not be a problem if this agreement can be signed, because this is not in public, it's in factory environment. And use the electrode properly can prevent the potential accident. Because if the operator is scared, that data will be instantly collected and the robot will be shut down. So that's something very promising to use this. But also people talked to me, then in a factory environment, I cannot freely think about anything. Whatever I'm thinking is detected by the system. There's no privacy. I cannot even think when I meet my boss, how reaction should I take? Is that good or bad? Don't worry about that. Is in a factory environment, is work related. That should be guaranteed, but this will take a long time. And if this is required, not only is the factory training part is needed, perhaps university training is also needed. The curriculum need to be modified to include this. It already happened. Nowadays, we use lots of digitalized approach, use AI, use machine learning. Traditional mechanical engineering and industrial engineering alone is not sufficient. In the factory in the future, we need a data scientist and need a computer scientist as well, or this can be combined together in an interdisciplinary educational program. The student can be an engineer, can be a scientist at the same time, can possibly process large amount of data in the digital world. So this is a requirement. How to design a gear may not be that important. You can buy it directly.
Okay, thank you, Professor Wang. We have two questions from Hong Kong U. The first one is Tim. The question is, do you think the brainwave-driven robots will be prevalent in the coming few years? What would be the most promising applications driven by this technology in the near future?
Yeah, it's related to the previous question. I guess you typed in your question at the same time. And in the next few years, the research is still focused on the fundamental breakthrough, how to understand the brainwave, how to process them properly. There's many different processing algorithms to remove artifacts, to identify patterns, to extract the features and do classifications. So if many colleagues or friends work together, perhaps we can find most reliable, most accurate algorithm for this processing, and also to help for the hardware development, middleware development. And I see the most useful application area for myself is a human-robot collaboration. It can also be used for ergonomic analysis when worker working in an environment very close to robot. This mental load, cognitive load may increase. And those can also be detected and analyzed and used for this factory planning and control. The other area more mature to use a brainwave is in the marketing area. You have a new product. This product needed to be put together in an advertisement. So for the viewer, look at it, you can detect whether it's a positive reaction or negative reaction based on brainwave. So you can modify the design to have the message best penetrated to the viewer. So that's quite a different application potentials.
Okay, thank you. The previous question is from Dr. Kevin Kerrigan. It's Advanced Manufacturing Research Center, University of Sheffield from the United Kingdom. Thank you so much for the question. And following the question is from one of my PhD student, Mr. Zhang Yishuo. He is a PhD student from our department. He would like to ask, the robot controlled by brainwave can be used in assembly industry, such as the construction on-site assembly. How could be ensue the safety problem and assembly quality? Operators' brainwave sometimes is unstable, but assembly in industry has a high requirement for the installation precision, and there are many associations and constraints. Is there any method to control the risk and ensure the quality of the assembly based on the brain-controlled robot? Professor Wang, please.
Very good question. And brainwave alone cannot solve the problem entirely. I mentioned earlier to use a gamma wave to detect whether a human is being scared, but that might be too late. That's the last resort to protect a human. If this outside field environment can use a camera or some other type of sensors to detect potential risk, potential collision, we should also include that. Normally in factory environment, we use the cameras like a depth camera, kinect sensors to detect relative distance and relative speed between human and the machine, or could be a robot. And those speed of the robot is controlled by the relative distance. So if a distance is very close, the speed is also low. When you touch a robot, the robot is stationary. So this is monitored and controlled at all time, other than brainwaves. Brainwave is just something suddenly happen, and other system is not possible to protect or detect in advance, then robot can be triggered as an emergency stop. So that's we have to use a combination of a different technology and use a redundancy of a different sensors to protect the environment. Again, brainwave alone may not satisfy the operator. That's a limitation.
Okay, thank you. Sorry, Vincent. I saw your questions actually both from the Q&A and the chat channel. So his question is, Professor Wang, we submitted a manuscript to our theme for our publication trail with 6 references from our theme some days ago. However, our theme rejected with the comments as out of the scope. how should we deal with this issue? Thanks.
Yeah, I guess it's a different Vincent. My colleague is also Vincent. Well, anyhow, authors are encouraged to cite own journals to show the relevance. Sometimes they publish the paper maybe on the boundary of the scope of the journal. So because everyone's research is unique, you can find some similar research to support you, but those research may not be exactly the same of yours. Otherwise, you cannot publish your paper. I can select 10, I can select 100, but that doesn't really justify the paper is 100% fit. And for our theme, there's one focus is a manufacturing application. On the surface, you think your work is on robotics, and then you submit it to it. If in the paper is on the fundamental of robotic research, there's no any relevance to manufacturing operation or how robot is used to help manufacturing operation, it will be considered out of scope because there's many pure robotic related research journals is more suitable just to focus on robotic mechanism design or is a characteristic of a robot parameter identification. Those will be considered out of scope. So it's very important to show the relevance. Your work can help manufacturing operation. Our theme is a manufacturing journal.
Okay, I hope the comments or reply to Vincent is useful. And another question is from the chat is the Diana Chester, BWC. Do you know of anyone who is applying this brainwave control technology to medical rehabilitation, such as using a robot to help a patient who had a stroke or spinal cord injury?
Yeah, this is relatively popular. There's many institutions doing this, universities, different research group use brainwave robots to help in this area. And especially, for example, for the wheelchair control, there's some prototype. I forgot the name of the university. They can use a brainwave to control wheelchair because the patient sitting on the wheelchair has no ability to navigate and steer the wheelchair. So that's possible to use in this area. Similarly, it can be used for rehabilitation purpose. So if you do some search online, I think you can find quite a few. Last time I visited university in Wuhan, I saw a group of people is working on this area. Another area could be used in exoskeleton and to control your exoskeleton in a battlefield. That's something far away, but it's still ongoing research.
Okay, I think the answer is sufficient. If you have
very good question.
Yeah, if you have more questions, please feel free to ask. Thank you. We have three more questions, or four, sorry, from Q&A. And Simon NX Zhang, dear Professor Wang, thanks for your sharing. May I ask that are the EEG signals collected by dry electrodes reliable? Have you ever seen some researchers use that device to extract movement intentions? Thank you.
You mean the dry electrode, right? Basically, there's two types. One is dry, another is wet. Wet use a gel or some special liquid to get a better conductivity between human skull and the electrode. Dry electrode doesn't need to apply any of those liquid or gel. However, the reliability is relatively low. If you only have several sensors, you can use dry. And possibility is there's a relative movement between electrode of yours and your skin. And that tiny movement will generate lots of noise artifact. So that's a drawback. Most of the popularly used one is wet. Use either liquid or use a gel to have a better conductivity, especially for people with a thick layer of hair. Without a gel, it's very difficult. Is that the question? Hopefully I answered your question.
Okay, thank you, Professor Wang. The following question is from Kam Kai. It's one of our PhD students in our department. His question is, does the emotional signal significantly affect the performance of robots? Do we have any requirements for workers? Because some workers may feel upset or sad sometimes, which may have negative effects on controlling robots at that time.
Yeah, this is a difficult one. If the operator is professionally trained, this emotional thinking in the head should be put aside and only use the trained data to control. Otherwise, those emotional information or thinking in the head will be the noise, and the noise level will be much higher than your control command. Eventually, the system will not work. So that's the drawback. However, if this emotion is related to working condition, this system can help. The working condition may not be good enough. It's the speed is very high. You feel pressured, then this signal can be used to slow it down. Or if you are not satisfied to the certain condition related to noise or sound, this can also be analyzed and use your brainwave to control and to improve the working environment. So it depends on how you want to use the brainwave signal. In the other case, is how to remove those emotion-related signal, consider them as a background noise, and identify the true thinking you want to use to control robot. This is itself is a research area. Not that easy.
Okay, thank you. Next question is Professor Wang. What's the major reason of a paper rejection and potential acceptance? This question is from Zexin Xu.
Rejection, there's multiple reasons for a paper to be rejected. The first is out of scope. Second is obviously it's a low quality. So those papers will be rejected without a review. And then it goes to the review process. And this is a people process. Normally we use 2 and more reviewers to judge the merit and quality of one paper. If reviewers are not in favor of publishing your work, then it will be rejected. Sometimes the paper will be given a second chance for a major revision. And once your paper is received a major revision decision, use this opportunity wisely and carefully revise the content and address reviewers' comments one by one and with a very detailed, polite answer. So this response or revision notes is very important. provide all the details. Sometimes you may not agree with the reviewers. It is possible to put a strong argument, rebuttal. It is okay. And if you believe yourself, you're confident, provide all the details, evidence, you can counter-argue. And the reviewer may not be the expert in your domain, possibly misunderstood. So this is a back and forth. As long as you are not stick into your opinion, your perspective, you focus on the fact and the truth, eventually the paper will be accepted somewhere, even if it's not from the same journal. That's why if your paper is being rejected, you are encouraged to improve it, submit it to another journal. There's no penalty for that. Again, there's no better approach to judge the quality. We have to use the reviewers. And reviewers, in most of the cases, as I see, they base it on their own experience, own knowledge, and sometimes their own opinion. If they use their opinion, it's quite subjective.
Mm-hmm.
So that's a human process, and we have to live with this.
Mm-hmm. Okay, I think we may take the last question due to the time limitation. This question is from Wennan Zhang. She is one of the PhD students in our department. The question is, EEG will be affected by coughing or blinking. I would like to ask how to avoid these effects to analyze brain EEG signals, show the potential in using the signal for HRC.
Mm-hmm. Yeah, coughing is obvious, and eye blinking, those signals are very strong. Normally based on frequency and amplitude, this can be removed. They are considered as artifact, can be removed, or that section will be removed as well. So in practical use, the best approach is you do not cough and do not eye blink in that a few seconds when you issue the control command. Otherwise, you wait after you coughing, eye blinking, then start to issue the control command. And when to issue your brainwave-based control command is at your hand. You can control the system to start and stop. And only take a few seconds. I think most of the human being can hold without eye blinking in 10 seconds. And you can use that period to control the robot. Or for the training, you can participate in this competition to see who blink first. And for someone can last for five minutes without blinking. So that's kidding.
Mm.
And for training, it's the same thing. Training normally takes about 10 seconds. Within that period of time, try to avoid coughing and eye blinking to get trustworthy signals from your brain. That's what I can recommend.
Mm. Okay, thank you so much, Professor Wang. So finally, I will remind everybody. So during this pandemic, actually our department prepare a very rich meals and from the knowledge perspective of view to all the academic student colleagues all over the world. So Professor Wang, this is the third seminar series, and next week we have Professor Shen, Zhongjun Shen, Max, is from the UC Berkeley. He will give a talk on the practical end-to-end inventory management model with deep learning. So I'm looking forward to see you guys again next week. And also we have the Professor Ren Long and from the editor-chief of TRI, and Alexandra Dogui is IGPR editor-in-chief, and Professor Steven Newman from IG AMT. IG same. Sorry, it's too late. I'm so tired. So I'm looking forward to see you guys in the coming seminar series. And thank you so much, Professor Wang, the support and your brilliant presentation and your patience to answer these questions.
Thank you for your invitation, and thank you all for your participation and listening and discussion. I hope if you have a further question, you can send me email and we can discuss separately. Thank you.
Okay, thank